Hello everybody, on behalf of a couple of potential clients we have in the Aberdeen area, we're just going to run a quick ISO 5167 orifice plate calculation based on AGA 8. I'm going to open the CONVAL toolbox, the differential pressure flow element calculation. I've pre-populated the AGA 8 gas, but I will show you where that is. CONVAL stores their records in a file-based system, not in a database. So this means all the files and records are easy to file and store. So there we go. I'm going to give it a tag number. Strangely enough, it's the same name. We can pick lots of different fluids and phases. I'm going to very quickly show you one that I've pre-populated. I'm going for an AGA 8 gas calculation. I have pre-populated the gas. Here's DPF AGA 8. If I click new, you would get the same window pop up, and you can you can populate these components. If your component mixture didn't add up to 100%, I can click normalize and it will adjust all the values. So very quick and easy to achieve. I'm going to pick 30 bar, operating temperature of 15 centigrade. You can expand each of these sections out to see and view more detail. You can see our real gas factor there. Scroll down. In terms of pipe material, have a huge selection of different pipe materials, or I can quickly enter a known pipe material. I'm going to just pick A105 for now. I'm going to say it's cold drawn, so this is our pipe roughness. I'm going to pick a ANSI 6-inch standard weight pipe. I've already got an error warning there, so I'm going to go for class 300. I'm going to change my unit scheme on the pipe work to millimeters. And hey presto, that's my pipe work information entered, and we've got our thermal coefficient linear expansion. I look at my flow element. Again, same sort of thing, but I'm just going to pick a 316. I'm going to do a Daniels calculation here for Daniels fitting. It's a flange tap device. I'm going to calculate out the bore and the beta ratio. I'm going to calculate for a differential pressure of 250 millibar. Oops, sorry. 20,000 cubic meters an hour. And hey presto, we've got a beta ratio of 0.58. Just going to change that now to differential pressure, and I'm going to make this a sensible bore. For machining purposes, you can see we've just got a slight tweak on the differential pressure there. Just a quick bit on standards. If I expand this out, you can see we're calculating to 516 2022 edition. I can change the year and I can change the standard. If I look at my outlet, we can see the straight run requirement and also the additional 0.5% error. I can change that to pipe diameters. We can see the outlet section there, and I can go to the uncertainties, click the extended uncertainty calculation. I'm just going to put some zeros in here just for speed. A temperature 0.5%. We're going to use an IDP50S, beg your pardon, a gauge pressure version, one of the new error statements, and we're going to put our super duper differential pressure error in there. We're going to assume we've got perfect density measurement, and hey presto, we've got a error statement for our maximum flow for a single pressure transmitter with an error of full scale. So I'm not going to calculate the error of reading at this stage. So to simulate one of your other high performance transmitters, you can also see the sensitivity coefficients here. I'm going to quickly calculate out the mass flow error over a 10-to-1 turn down. So volume flow rate 2,000 to 20,000 quickly see what our error is without any additional pressure or temperature errors built in. Give me a second whilst this calculates. It takes a second with the number of computations it's having to do in the background on my laptop that is running at least 10 other packages at the moment, including a video capture. Another 5 seconds. Okay, another 5 seconds. There you go. There's your error curve for 20,000. You can see we've got a couple of parameters here. As I scroll up and down the range, we can see that error statement here scrolling. So we've got 20,000 full scale. If I come down to 2,000, we've got an error with our new super duper transmitter of 0.98%, so pretty tight. But you can see how CONVAL is calculating that out quickly and easily. We could add an additional calculation. I'm not going to do that for this video because I don't know how long that's going to take, but we could put in, for example, different pressures or orifice sizes, huge number of different calculation functions we can do. I'm going to save that with a graph. Here you have a dynamic help, so wherever you click, wherever you click, you get changing dynamic help functions. So in here, talks about the material, in here talks about the beta ratio. Have an overview here of what we're doing to complete the calculation. We've got a number of uncertainties listed here. We've got a graph associated with the calculation. I'm just going to save that quickly. Save it in my drafts. Where are we? Save it in downloads here. OP Calc, there we go. And a couple of other things. We can print the file. We can export it. We can export it to a flow meter data sheet. We can export the calculation. I will show you all of that at another time. That concludes my very quick demonstration of an orifice plate sizing to AGA 8. Thank you for watching.